Hi friends, welcome all. In this video, we are going to define some new concepts in complex analysis, and the definitions we are going to define are one is interior point and another one is open set. In the first video, we have defined the concept the neighborhood of a point, and we are going to define the interior point in terms of neighborhood of a point. Now we can look at what interior point means. The interior point in the complex plane is with respect to some sets in complex plane. The interior point is defined relative with respect to a set. That means if we are given a set, we can define the interior point of that set. So we can look at the definition of interior point. And the definition says that if we are given a point z0, a point z0 is said to be an interior point of a set S in the complex plane. That means we are given a set S in the complex plane and a point Z0. Then we say that the point Z0 is the interior point of the set S in the complex plane if there exists some neighborhood of Z0 that lies entirely in S, entirely within S. That means a point Z0 is said to be an interior point of a set S in the complex plane if there exists some neighborhood of Z0 that lies entirely in the complex plane. In the case of complex analysis, what we mean by the neighborhood of a point? That means if we are given a point Z0, we can find a open disk. We can find an open disk that is completely contained in the set S. That means let S be this set, a random domain in the complex plane. And if we consider the point Z0 in this set, then we can find an open disk of small radius that is completely lies inside the set. Therefore, this point is an interior point of the set S. Now, if we consider the point outside the set, if we consider the point S on the boundary of the set, then for any open disk of small radius that contains the points inside the set also outside the set. That means any open disk of small radius contains the points outside the set. That means we cannot find an open neighborhood, we cannot find an open disk that is completely lies in S. Therefore, this point is not an interior point of S. If we looking into the real number system, what we will get? Instead of open disk, we will get open neighborhoods. If we consider the points in the real axis, if I am considering a point here X in the real axis, then X is said to be an interior point of some set S in R if there exists an open interval that completely lies inside that set. In case of complex analysis, the open intervals becomes open disk. That means open disk means a neighborhood of that point. We can look at some examples in real cases and some examples in complex cases also. If I am considering the set of real numbers, if we consider in the set of real numbers, any point of R is an interior point of R. Since if we consider a point X belongs to R, we can find an open interval that completely lies inside R. Therefore, any point in real axis in real number system is an interior point of R. Instead of R, if we are considering the set of rationals in real number system, and let X belongs to Q be some point. What about X? Is X an interior point or not? If we consider a neighborhood of X, that means if we consider an open interval about X, that interval must lies points outside Q. That means that interval must contains the irrational numbers. Therefore, there does not exist any open interval about X such that it completely lies inside rationals. Since rationals and irrationals are dense in R, if we consider any open interval of small radius, that open interval must lies the points outside the rational numbers. Therefore, we cannot find any open interval that completely lies inside the rational numbers, and therefore any point of Q is not an interior point of Q. And in case of complex number system, I am defining the set S as the set of all Z such that real part of Z is greater than 1. Then we can mark the points in the complex plane as real part of Z is greater than 0. Therefore, if we fix Z is equal to X plus Iy, X is equal to 1, as the real part of Z greater than 1, we will get the region like this. The right hand side of X is equal to 1. And if we consider any point in the set S, if we choosing a point here, here real part of Z greater than 1, therefore the points on the line X equal to 1 does not lies inside the set S. Therefore, if we consider any point in the set S, we can find an open disk. We can find an open disk of small radius that completely lies inside S. Therefore, all the points in the set is such that the real part of Z greater than 1 is an interior point of the set. If we considering real part of Z greater than or equal to 1, therefore the set includes the points on the line X is equal to 1 also. And if we choose the point on this line, and if we consider an open disk around this point, that open disk must contains the point inside the set S and the outside the set S. That means we cannot find an open disk of small radius such that completely lies inside the set S. Therefore, the point is not an interior point of the set S. So there are some sets such that all the points may be interior points. Some points may not be interior points. Any of the point may not be the interior point of the set. If the considered set every point is an interior point, then the set S is said to be an open set. That means if the considered set S satisfies the property that every point of the set S is an interior point, then we say that the set S is an open set. Therefore, an open set means every point of the set S is an interior point, then we say that the set S is an open set. In the considered set, if we consider S is equal to real part of Z greater than or equal to 1, here the points on the boundary line x is equal to 1 is not an interior point of the set S, therefore this set is not open. Instead of real part of Z greater than or equal to 1, if we considered the set consists of the points Z satisfying real part of Z greater than 1, then every point of S is an open, every point of S is an interior point of this set S, therefore S is an open set. If we consider in the real case, R is an open set since every point of R is an interior point, and Q is not open since any point of Q is not an interior point. If we consider any point X belongs to Q, or there does not exist a open interval satisfying the property that completely lies inside the set Q. Therefore, any point of Q is not an interior point, hence Q is not an open set, but R is an open set. If we consider real part of Z greater than or equal to 1, therefore every point of this set is an interior point, and hence S is an open set. Therefore, in this video, we have defined new two concepts in the complex plane, and first one is the interior point of the set, and the next one is the open set. A point Z0 is said to be an interior point of set if there exists some neighborhood of Z. That means there exists some open disk of Z0 such that completely lies inside that set. Then we will say that the set S is an open set, and if every point of the set S is an interior point of the set S, then we will say that the set S is an open set. Therefore, we define the interior point in terms of the neighborhood and open set in the terms of interior point. Okay, we can wind up this video and we can meet in the next video with more definitions. Okay, thank you.